Welcome everybody. My name is Oscar Iglesias from the University of Barcelona, and today I'm going to present results of a study of nanoparticle assemblies for the use in magnetic hyperthermia. In particular, I'm going to show you the effects of dipolar interactions on the aggregation state of the assemblies on their performance for this application. What we are trying in this field is to try to find the optimal parameters so as to maximize the so-called specific absorption rate, or SAR, which is directly related to the hysteresis loop area. And we can tune the material parameters essentially by increasing the anisotropy volume or saturation magnetization of the particles, so that the hysteresis loop becomes wider and have a higher area. But any of these solutions faces its pros and cons. And in particular, we can see that as we increase the magnetic saturation or increase the concentration of the particles, then the dipole interactions increase because the particles will tend to form aggregates. And it's believed that the dipole interactions diminish the specific absorption rate. However, I could show you that by tuning the geometry and the way in which we place the particles in space, the dipole interactions can increase. These are at least we can minimize its effects. As a first example, I'm going to show you that the individual properties of a particle matter. As we showed in this study, cubic particles heat much more than spherical particles of the same size, which is an individual particle effect. And moreover, we saw also that the cubic particles tend to form linear aggregates in the form of chains, and whereas the spherical ones do not. And this can also be linked to the increase of the specific absorption rate, as can be seen here, a result of a simulation of a chain of cubes with dipole interaction in between. We see that increasing the chain length, the hysteresis loop area increases, which demonstrates that chaining and the shape of the particles have result in an increase of the specific absorption rate. So in order to better understand all this, we will perform, I will show you results of simulations of different configurations of a particle assembly, starting from chains characterized by particles of radius r, and separation characterized by the parameter lambda, which is 1 for particles in close contact. Then I will proceed to study regular lattices of particles, which can be considered an extension of the chain case with different aids. And finally, I will treat the more realistic case of having particles randomly distributed in space with different concentrations. For all the simulations, the material parameters correspond to iron oxides. I will not be varied. To start with, we have here the results of non-interacting particles hysteresis loop at different temperatures and 2 characteristic particle sizes. 4 easy axes are parallel or randomly oriented. We see that the small particles at the room temperature become superparamagnetic, whereas the bigger size particles are in the blocked state and therefore have a sizable hysteresis loop area. When we compare these results with chains of particles, in which we can tune the interparticle distance, lambda, we see that the interactions open up the hysteresis loop for the small particles, which were otherwise superparamagnetic. This effect is smaller as we increase the separation between particles, but still persists. However, for the 15 nanometer particles, the interactions are more relevant than for the smallest one, as we can the smallest ones. As we can see here, the hysteresis loop area increases far beyond what is obtained in the non-interacting case, and this sizable increase of the hysteresis loop area is relevant even for particle separations of 1 diameter in size. We can plot the hysteresis loop area as a function of the interparticle separation for the chains at room temperature, and we see that the hysteresis loop area lies far above, independently of the orientation of the easy axis, the value obtained for non-interacting particles of the same size, as you can see here. Moreover, the nanoparticle, as we increase the nanoparticle radius in the chains, the SAR increases even for randomly oriented easy axis in the assembly. Next, we proceed to the regular lattices of particles, in which we will vary the height of the geometry. And we have obtained the hysteresis loop area for different heights and different particle radius. But let's focus in this case. Let's focus on this case. What we see here is that when we increase the interparticle interactions, decrease the interparticle separation, depending on the geometry of the assembly, planar or more elongated, like in this case, the SAR may increase in these more elongated geometries, but decrease if the geometry is closer to oblate. So the SAR can increase or decrease due to the foreign interactions, depending on how we distribute them in space, if they are placed in a regular lattice. Moreover, we can see that the SAR is not always maximized for close particles in contact. See, these black regions or darker regions are not always found at lambda equal 1, and the same happens for random anisotropy. Next, we will proceed to a more realistic case of random assemblies, and we will study the role of the concentration on the hysteresis loop area. The excuse here is that experimentally we can deliver the particles to the cells encapsulated inside, for example, like liposomes, like here, or at the surface of them, and we can control this experimentally. Moreover, we can control also the aggregation state by the chemistry of the nanoparticles formation. And we can see that we can control the number of particles that form clusters when they aggregate. So we are going to consider the results of simulations for particles placed at random inside a spherical cavity, at random at the surface of a spherical surface, which and also when they aggregate, forming clusters of 3 nanoparticles. You can see here typical hysteresis loops for the aligned case, and what we see here is that in any of the cases, when increasing the concentration, of course, the coercive field and remanence decrease, and therefore the hysteresis loop area decreases. But when we compare the hysteresis loop area of particles deposited on the surface of a sphere, inside the sphere at random, or the clusters, what we see is that in the case of nanoparticles located at the surface of the sphere, this means attached to the liposome surface or attached at the surface of the cells, the SAR is much higher than when we have the particles inside the liposomes or internalized inside the cells, which means that maybe it's not necessary to internalize the particles inside the cells. Having them attached at the surface will heat up much more and destroy more effectively the cancer cells. We see that clustering in between the particles seems to reduce the SAR very drastically, even if these clusters are only of 3 nanoparticles, which means that independently of the concentration, which means that when we have clustering, the interparticle separation inside the cluster is what dominates because the concentration has no effect on the SAR. So in the case of aggregation, that we have clusters of 3 particles, we can increase the area of the hysteresis loop if we coat the particles with some surfactant, even having clusters, but now of particles separated by some cutoff distance. When we increase the thickness of the surfactant or the cutoff in the simulation, we see that the area and therefore the SAR increases. So we can minimize the detrimental effect of clustering or an aggregation if we fine-tune the interparticle distance in the clusters by capping them with some surfactant. Moreover, we can ask ourselves if a random distribution of particles inside a sphere or placed inside an ellipsoid, like elongated in the direction of applied field or elongated in the perpendicular direction, will have the same heating capacity, and we see that this is not the case. Surprisingly, what we see is that if we're able to randomly distribute the particles, doesn't matter if the anisotropy axes are aligned or not, in a region of space which is elongated in the direction of the field, the SAR will be much higher than placing the particles at random in a spherical region. So the SAR values can be made to approach the non-interacting case if we are able to distribute the particles inside more elongated regions. So with this, I end up by concluding that the individual properties of the nanoparticles, such as the shape and the size, have an impact on the hysteresis loop area due to the surface effects and changing the anisotropy in the reversal mechanism. I have shown you that in order nanoparticle assemblies, the role of dipole interactions depend critically on the spatial arrangement of the nanoparticles and also on the way that the assembly is elongated or the shape of the assembly itself. Whereas for random distributed assembly, SAR is always diminished with the concentration, although the interaction effects can be minimized if we're able to place the particles at the surfaces or confined in elongated regions. So with this, I conclude, and I thank you for your attention, and I'm open to any question that you may have.